AI is a powerful tool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Welcome to today's AI for Manufacturing webinar. My name is Li Hui Wang of KTH, Royal Institute of Technology in Sweden. I'm honored to moderate this webinar. The topic of today's keynote is Cyber-Physical Internet, CPI, sending and receiving manufacturing products, just like sending and receiving instant messages. We are fortunate to have Professor George Huang with us today. Let me introduce George Huang first. Professor George Huang is a chair professor of smart manufacturing at the Department of Industrial and Systems Engineering, the Hong Kong Polytechnic University. He gained his BE Eng and PhD degree in mechanical engineering from Southeast University, China, and Cardiff University, UK, respectively. He has conducted a research project in areas of smart manufacturing, logistics, and construction systems analytics through IoT-enabled cyber-physical internet with substantial government and industrial grants exceeding 100 million Hong Kong dollars. He collaborated closely with industries through joint project and startup companies. He has published extensively and his work has been widely cited by research community. He served as associate editor and editorial board members for several international journals. He is a chartered engineer, fellow of ASME, CILT, Hong Kong IE, IET, and IISE. Ladies and gentlemen, without further ado, please join me in welcoming Professor George Huang to the virtual podium. George, the floor is yours.
Thank you very much, Professor Wang, for introducing me. I will share my screen. Right, this is George Huang from the Hong Kong Polytechnic University. I'm very pleased to have this AI for Good platform to give this seminar. The seminar presents and discusses our recent research project on CPI, as the subtitle indicates, we hope to use CPI to send and receive objects and goods, just like sending and receiving instant messages using WhatsApp and WeChat. In 1960s and 70s, researchers borrowed good ideas from post office operations to develop the internet. Today, through this project, we follow internet features to modernize and revolutionize the global logistics systems. The result will be a cyber-physical internet platform. Now, this talk is based on a theme-based research project recently awarded from the Hong Kong Research Grant Council. The Synchro Hub project is jointly conducted by the Hong Kong Polytechnic University and the University of Hong Kong. In addition, we have Jinan University and Shenzhen University in the Great Bay Area. Overseas collaborators come from Paris and Technical University of Delft and Georgia Tech. So the participation and the support from industries and business associations are greatly appreciated. Now, the project is conducted in the context of Greater Bay Area, which is in the southern part of China, for several reasons. First, GBA has been the so-called factory of the world for more than 2 decades. Because of the manufacturing activities, so the GBA is also a powerhouse of global logistics. You can see the strength of both manufacturing and the logistics with the figure under the red sentence below. And also, cross-border import and export logistic activities are probably one of the most intensive in the region. Trade and the logistics industry is one of the 4 economic pillars in Hong Kong. Finally, the region has some kind of first-class logistics and transportation infrastructure, including 3 major airports and 3 shipping container ports, and also 3 major high-speed railway stations. But nevertheless, this excellent infrastructure still suffers from the challenges caused by disturbances and the disruptions for those something like caused by the COVID-19. So for the past 3 years, starting from early 2020, we suffered from 5 waves of COVID-19 in Hong Kong. So each wave affected seriously our logistics industry. For example, like city lockdown, factory shutdown, flight cancellation, seaport blockage, and cross-border shutdown, and also the railway blockage due to the war in Europe between Russia and Ukraine. So the shipping container price index has increased 5 to 10 times. Air cargo container price has increased 5 times, and there are serious shortage of logistics supply, and oil price has risen substantially. So the demand for logistics has actually increased, but the capacity was limited, and also because of the uncertainty, the availability of the logistics capacity is unknown. So the cost and the lead times are very high and fluctuating. So during the early time in 2021, some companies came to talk to us to renovate or improve their existing global logistics systems. So this project was actually motivated by those industrial companies to establish new smart logistics systems. Okay, so some companies tried to move from sea shipping to air cargoes, but because of the flight cancellation, they cannot use air cargoes. And also the capacity of air cargo capacities are very limited. So they changed to train, but because of the war, the trains were stopped as well. So the company really had a difficulty time. They don't know what is happening, what goes wrong, and if there's something goes wrong, which tier, which mode, which leg, which border, which hub, regardless of the excellent infrastructure, and these problems still are apparent and affected our industry in Hong Kong and globally. So there are basically two ways to solve the problem. One is to further develop our transportation and the logistics infrastructure to enhance the resilience of the system. The second approach is the approach we adopt in this project. Okay, so actually there has been major effort in Europe to convert or to develop physical internet to enhance the resilience of the global logistics system. So as early as 2010, there was a major EU project under Framework 7, which is called Modulariska. It is the first major project to develop physical internet. The idea was to develop a logistics system that sends and receives goods, like sending and receiving emails. The idea started early on in 2010s. Since then, there has been 10 major European projects related to physical internet. Significant efforts have also been made in Hong Kong and also Japan. And Europe has made a dramatic achievement and progress through those projects. They established a roadmap for the physical internet for the next 25 years or 30 years. You can see the roadmap include 5 dimensions here. We can see there is no dimension explicitly related to digital internet. So if we are going to follow the internet features for logistics systems, then this project here, the new project here, adds a digital layer or digital dimension for cyber-physical internet. Therefore, we should be able to develop and enjoy something like a ping command available in the internet for logistics systems. So that's the basic idea to add one digital dimension. Okay, so based on that observation, this project is aimed at developing a CPI platform, which is basically something like WhatsApp or WeChat platform but for sending and receiving goods. We propose 4 pillars of innovation. So the upper left is the digitization architecture. Upper right is the network protocol lower right is the value proposition, and the lower left is decision analytics. So I will go through each pillars one by one. Now, the first pillar is the digitization architecture. Under this pillar, we focus on several research tasks and deliverables. The first one is digitization. Is the ultimate outcome of digitization is to create digital twins. Both digital twins and physical twins are used to create what we call the meta object or cyber physical objects, or simply called meta twins. The names don't matter, but meta objects are very special because it has 100% digital characteristics. They are data. And also they have a 100% physical characteristics. So the idea is to use the internet to deal with the data characteristics, and we develop new protocols to handle the physical characteristics. Like all the other research groups, we apply the three-layer digitization architecture. At the bottom are physical objects or physical twins in logistics systems. So at the top are digital twins. In between, we have the cyber physical connectors, basically are smart IoT devices. So we deploy IoT devices to turn these physical objects into smart objects, and then we use the cloud agents to encapsulate those smart objects into digital twins. So together, digital twin and the physical twin create what we just described as meta objects or meta twins. Okay, because of the time, I will not explain the details. So we use that digitization architecture to convert the warehouses into cyber physical warehouses. We can also convert the shipping container ports into cyber physical ports, and also airports into cyber physical airports or meta airports. Okay. Now, one example is to convert this truck, which is a typical facility in logistics systems, using all these sensors into smart truck. And then we use the cloud agents to encapsulate them into a cloud truck or digital twin truck. So on the right-hand side, we will have the cyberspace where we make decisions and control the physical meta object or meta truck here. Now, the setting up cyber physical truck, smart truck in cyber physical internet is just like setting up a printer with our computer on the internet. So basically, we have two levels. One is to set up truck meta twin in the cyber CPI network, the location like the IP addresses, where is the printer or where is the truck. Okay. The second is to set up or configure how the printer works. In this case, how the meta truck works. Okay, basically the same thing. We are developing this utility systems for configuring and setting up the meta trucks on the CPI. Okay. Now, we also use industrial blockchains for several purposes. First, we use blockchain to share information and services through the network. And also we use the blockchain to create, establish cyber-physical visibility and traceability. We also take advantage of consensus and incentive protocols embedded in blockchain to establish mechanisms for CPI network. And we also take advantage of security and authenticity mechanisms inherited from the blockchain technology. And finally, we use smart contracts to define and implement all these four mechanisms. Okay, so that's the first pillar of innovation. Let's move to the second pillar of the innovation. The second pillar is about network protocols. First of all, we propose CPI network configuration protocols. So like in the internet, we have the CPI LAN, CAN, and WAN. CPI LAN basically is a local area network, but for logistics, okay, for logistics. For example, this slide shows the prefabricated construction logistics. On the left-hand side, modules are produced in the factory, and they are moved to the warehouse somewhere close to Hong Kong side, close to the border on the Hong Kong side, and then modules are distributed to construction sites in different regions in Hong Kong. So we define three types of networks. So on the left-hand side, we have the wide area network for first leg module logistics. On the right-hand side, we have the catchment area network for last leg logistics. So in the middle, because this network is within the warehouse, so it's local. So it's we call it local area network. So by defining these three different types of network configuration protocols, then we can propose and develop the specific technologies for managing these different networks. Okay. The second deliverable is the CPI's TCP PIP protocols. So on the left-hand side, because meta objects have 100% digital characteristics, therefore we use the internet TCP IP to deal with the flow of data, exactly the same, okay, for dealing with the digital characteristics. But because the meta objects have 100% physical characteristics, therefore we have to propose and develop a new set of standard and protocols. We call it CPI TCP PIP. Note PIP, not IP. So this PIP stands for physical internet protocols for dealing with the flow of physical materials. So this is something new we are developing for CPI. Okay. The third deliverable from the second pillar is the TCP/IP protocols, similar to the third level is the network level. Okay, this is the TCP/IP hierarchy. So in the middle is the network. So in CPI, we also have the network. But in internet, we have the data packets, which are the standard container for the data. So for CPI, we have to develop the standard containers for the goods or the objects. So we can use trucks or container or pallets or trolley or boxes as the standard container. For the moment, we have serious debates in the European research community and other research community, which container should we use as the basic logistics packets, just like the data package in internet. But it doesn't matter which we use. We use a logical good container or packets as a packets, okay? It doesn't matter what it is. As long as we have a logical definition, that's efficient. So for the logistics packets at the network level, we can assign IP addresses for the sender and the receiver and some general descriptions about the packets, exactly the same or very similar to the data packets on the internet. So that's the third deliverable. Now the fourth deliverable, similar to the internet, are the routing protocols and the including routers and the routing tables. This is a very, very important concept in CPI. Okay, it's the foundation that will revolutionize the CPI or global logistics. It also let's see how this works. Now, this slide shows actually the process of sending an email from the left-hand side, the sender, and right-hand side are receivers. So between the sender and the receiver, we have a different routers in between. So for each router, we have the routing table here. So the routers actually use routing tables to find the optimal path to send this email from the sender to the receiver. So this is how the internet works. Now, next slide demonstrates how the cyber-physical internet works to send the goods from the sender on the left to the receiver on the right-hand side. So now traditionally, we have freight forwarders in between the sender and the receiver. Freight forwarders are basically businesses or companies that work together to identify the optimal path for sending the goods from the left to the right. Okay, so this project proposes the hardware routers to replace freight forwarders. Okay, and also we propose to establish routing tables and algorithms to automatically generate the optimal path for sending the goods from the sender to the receiver. Okay, so this is the biggest change, and also this CPI will change the ecosystem of the global logistics. The change is replacement of freight forwarders by hardware routers, CPI routers. So the last deliverable from second pillar includes some network, CPI network kernel services. The first three are very similar to those services available for the internet. The last one, the dark red component, is very unique for global logistics. We have the CPI alliances services. Okay. In logistics industry, companies and businesses are basically working together to form alliances. So it's like a domain, but different business domain. So in CPI, we will have to develop this business-oriented alliance services, which is unique in CPI. Now, let's move to the third pillar of innovation. It's the value proposition for CPI. We will cover 3 or 4 components. The first and the most fundamental value proposition of CPI is traceability and transparency. Now, on the left-hand side, I listed some of the traceability and the transparency commands available on the internet. Okay, and these commands are already available for transportation and the logistics. So for example, on the right-hand side, I captured a Google map, which I use for a walk to a park, from home to a park. Okay, so the Google map already indicated a few possible paths from home to the park, 3 possible, including the time and probably the calorie consumption if I walk. Okay, so the CPI traceability and transparency services will provide something similar for global logistics. Okay, something like the one I demonstrate on the right-hand side. So that's the first value proposition. The second value proposition is the spatial temporal value. So in order to have the traceability and transparency, we needed to reason about the spatial and the temporal characteristics of the object. It's a metal object in both cyber and physical spaces. Okay, so now for outdoor spatial temporal reasoning, we can use GPS or Beidou navigation system. But because many parts of the logistics operations take place indoor, especially local area network. So we must have an indoor positioning system. But indoor positioning system is very complicated. If the configuration of the space are different, then we have to calibrate and recalibrate the satellites, indoor satellites or gateways, we call. Okay, so we are developing an indoor positioning system with a genetic self-learning algorithm that will not require calibration. Okay, the indoor positioning system will use all those networking message signals like Wi-Fi, Bluetooth, UWB, 5G, and also GPS signals, or their combinations. So this is the most fundamental analytics to establish the traceability and visibility. The third value is the transportation service procurement trading automation for the CPI marketplace. Basically, CPI is a marketplace for those logistics providers, service providers, and service consumers, and also the solution providers along the CPI. So we propose the auction mechanism for the buyer or the shipper, or the seller or carrier to establish their businesses. So in this case, the seller and the buyer will be represented by their routers. So the routers will implement the auction mechanisms on behalf of buyers and sellers to establish the buying and selling businesses. So once that buying and selling business is established, then the optimal path is established from between routers. Okay. Now the fourth value proposition is a partnership incentive between players, stakeholders involved in CPI. One example is all the players, business partners, have to provide data in the CPI network for other business partners to share. Then one basic question is, why do I invest in digitization technologies to collect data and share data while the benefits, the other parties enjoy the benefits? So we have to provide incentives for all parties to share and use information throughout the CPI. So that's the fourth deliverable from the third pillar. Now, the last pillar of the project is the decision analytics. So once we have the CPI platform established, network established, then we expect all the decision models will be made very differently, maybe very different from those we are, for the moment, teaching through the textbooks, or some may be similar, but much simpler. So we choose 4 typical scenarios for our decision analytics. The first one is a continuation of prefabricated modular housing production logistics. Again, this diagram is similar to the previous one I demonstrated early on. So on the left-hand side, we have the one between the module producers and the warehouse in the middle. In the middle is the warehouse. So for the warehouse, we establish the line. On the right-hand side, we have the delivery services, just-in-time delivery services from the warehouse to construction site. Okay, so now we have conducted preliminary studies on prefabricated construction logistics, and this slide shows one of the optimization models. It's basically a standard mixed integer programming problem, but as we know, these models suffer from computational complexities and it's basically NP hard. So we hope we can use the routing tables and the routers to facilitate and automate the routing decisions within the CPI. Now, the construction logistics is much simpler than any other logistics. The reason is the construction modules are very large. So on each truck, we can only load 2, 3, or 4, usually very small number of construction modules. Therefore, the logistics packets, we can treat the truck as logistics packets. So it's much simpler. Now, the second scenario is slightly more complicated. It's the first leg export logistics. For example, like notebook computers, small electronic items. So they are first collected from factories using the trucks, and then send it to warehouses or the shipping container site or close to shipping container site. And then we send these containers to, say, the cross-border trucks or train, airplane or sea. So compared with construction logistics, these items are much smaller. So the combinatorial complexity is higher than construction logistics, but very much manageable, as the number of objects in each container is still limited and manageable. Okay. Again, we did some early preliminary studies without CPI. Okay. Again, it's a somewhat standard mixed integer optimization problem and suffer from a similar computational complexity. We hope to use the routing tables and the routers to again facilitate and automate the routing decisions. Now, the routing decisions are much more sophisticated in this case. It will include not just routing, but also the pricing decisions through the auction mechanism we just talked about. So the routing, auction, scheduling decisions will be made simultaneously through the auction mechanism. The third scenario is probably the most complicated scenario for CPI. I'm not sure whether or not we can do it. It's the cross-border e-commerce logistics. Why it is very complicated? The reason is the number of orders, the number of SKUs involved in e-commerce logistics are enormous. So the combinatorial complexity are very high, and so high that it's very difficult to manage them. Say, in each container, you have finite combinations, but the finite is closer to infinite combinations. So this is a very complicated situation. We will probably use the last mile delivery as an example to deal with the e-commerce logistics through CPI. Again, like most other researchers, we did some last mile delivery problems. This has been widely studied by different researchers all over the world. But all optimization models suffer from computational complexity. We hope, I'm not quite sure for the moment, okay, within the duration of this project, whether or not we can solve this problem. But at least we will extend our work from construction and export logistics for this e-commerce logistics, especially last mile delivery. Now, the last scenario is CO2 footprint through the CPI. Now, these slides show a case study conducted by our French partner in the Paris University, and they carried out the carbon estimation in France through simulation studies. So this is the mathematical model they used for generating these numbers. Now, this CPI project will propose a completely different approach to establish carbon footprint. Now, for the routing table, usually we use the distance. here as a matrix measurement here, indicator here, or the distances, time, cost as a column in the routing table. Now for carbon footprint, we can actually use the carbon equilibrium in the routing table, so that when we work out the routing decisions, we use these units to generate the total carbon emission through the routes or different routes and to minimize them. So because these units are available through the routing tables, so the computational complexity will be much simpler here, okay? And these units can be easily established. I just found out for the air ticket I bought recently, there is a carbon unit on my ticket. So this is exactly the number here. It's the number on my ticket. So say from Hong Kong to London, the unit of carbon emission is this amount. So if I transit from London to another city, say Paris, and then we work out the entire route and get the carbon footprint for my journey. Okay, so if these numbers are here already, then the calculation will be deterministic. Very simple. Now, we are coming towards the end of my seminar. I summarize the challenges and opportunities with the CPI. On the left-hand side, if we do not have CPI, like the 4 scenarios I presented, the uncertainty and the complexity of decision models are very high. Problems are usually stochastic and NP hard. Problem sizes cannot be big. They have to be controlled to obtain optimal solution, or we have to use heuristics to get near optimal solutions. Okay, that's without CPI. Now with CPI, all the objects and man-machine materials have real identifications. They have EPC, electronic product codes. So they have the real name throughout these CPI, cyber physical internet. So through these real identifications, we can establish cyber physical visibility and traceability. They are very important for look around decision making. So all the routers will have visibility and traceability. For example, like routing tables are typical example of visibility and traceability. So with routers can use them to look around among the other routers before making decision. Okay, and also we have the special temporal relativity and the reasoning. So in logistics, the spatial and the temporal values can be converted. Okay, so we have conducted some sensitivity analysis. So if you want more just-in-time delivery, then the spaces will be bigger. But if you targeted delivery, then the time window will be wider. So there's relative converging between the spatial and the temporal windows. Now, the fourth one, as I always emphasize, are the CPI routers and the routing tables. They are actually the implementation of visibility and the traceability. And they actually simplifies everything in the decision making. And also, because of the visibility, traceability, and the routing tables, then we can actually develop a theory of uncertainty postponement. So this is a great opportunity actually to work on. For the moment, because of uncertainty, everything is very difficult. So with the CPI, we can actually slice the time window, special temporal window, to very small unit. Within that small unit, everything is certain, but between units, there are uncertainties. So we use simpler decision models for the small unit, but use the iterative decision framework to deal with the uncertainty between the time window slices. Now, the CPI actually provide an opportunity for us, for both researchers and practitioners, to redefine the same problem. If the problem is redefined, then we can find much simpler solutions instead of using our traditional optimization problem formulation. Okay, so we also simplify and clarify boundary conditions, say between special temporal windows and also different metal objects through visibility and traceability. Finally, which is very important point, that we can develop minimalist solution algorithms. This is the important part. So far, our preliminary results indicates that the solution algorithms are much cheaper, which are quite often challenged by reviewers of our papers submitted to the journals. So the internet has changed the way of our work and life, but cyber-physical internet will change the way we send and receive goods for life and work. Okay, thank you very much for your attention. This is the end of my seminar. Thank you.
Thank you, George. This is a very interesting topic and an excellent presentation of very promising materials. So in this keynote presentation, Professor Huang presented the motivation, the goal of their research based on a project, and also shared with us the comparison between physical internet versus cyber-physical internet along the journey of research and development, including digitalization, protocols, value propositions, decision process, and finally shared with us the challenges and opportunities. The topic is about sending manufacturing products, just like sending and receiving instant messages. So now we open for discussions. You have the opportunity to send in your comments, your questions, just like sending an instant message. Use your chat box. Take your time to send in your question and comments. So when you are preparing your questions, perhaps I can start with a couple of questions from my side. George, you mentioned this, if it's possible to use a ping command to locate and know the status of a product or smart devices. This is very interesting. And sometimes the owner or the data or the device owner may not want to share 100% of the status. Just like in the internet, we can use routers, we can use a gateway, switches to build a subnet, and subnet sometimes is hidden. In the cyber-physical internet, how the data privacy or the granularity of the transparency is controlled and managed. Can you comment on this one?
Okay, thank you for this interesting question. And just like the internet, data packets has the header information. Only header information are shared among routers. Okay, the content in the data packets are not available or not shown to anybody. So similarly, in cyber-physical internet, only the data part, digital part, the header part, are available to business partners. The goods inside the container are not, the information are not shared among business partners.
Okay. Yeah, that's the way to treat the privacy issue. And because this seminar series or webinar series about AI for manufacturing under the umbrella of AI for good, I'm sure you use a different deep learning, machine learning algorithm to conduct the decisions process to decide what to do and how to do. Can you comment on the relevance of AI aspect to this very specific research, how AI is applied to manufacturing in this very specific project?
Now, the AI is basically, AI techniques are basically used in the third and fourth pillars of innovation. For in the third pillar, we have the indoor positioning system. We are using AI techniques, learning mechanisms to develop what we call the genetic self-learning algorithms to achieve a calibration-free indoor positioning mechanism. So this is a very data intensive, and also we develop quite unique genetic techniques. Basically, we define each location in an indoor space as a chromosome. Okay, so then we use the genetic operators for the incremental learning procedure. Okay, so eventually, the more we use the locating algorithm, then the more accurate it will become. So that's one aspect. Another aspect is the look around visibility and traceability. Okay, so say establishing the routing tables for routers. This is a pretty challenge. Okay, it's very much data driven. We needed to search for information like the auction result and the status of all the logistic facilities, and then to update the routing tables. So actually, we have three kind of time windows. Say the time window for the IoT sensors to collect data, and also the clock for stakeholder to make business decisions, okay, like auction, okay, and also the time window to update the routing tables. So among the three different time windows, the data will have to be dealt with very substantially. We are working on this. That's the second part of AI. The third part of AI would be incorporate data-driven decision models, decision analytics for the four scenarios, application scenarios we propose. Okay, with routing tables, we expect the algorithms would be much simpler.
Mm-hmm. Thank you. Now we have a number of questions already submitted from the online participants. You can also check your chat box. The first one is distinguished Professor Huang. What are the challenges for realizing spatial temporal traceability for MIC logistics?
It's 5 o'clock. Now, for construction spatial temporal traceability has to be separated. The discussion has to be separated. We separated them into one, LAN, and CAN. Therefore, we deal with the traceability differently. For example, like the one, then basically it's between the factory and the warehouse or the hub. Okay, so the traceability is relatively simpler because for each module we have the sensor attached to the module, and then for each truck we have also the IoT devices. So when you upload the module to the truck, then we establish the traceability at the factory side. Okay, and then the truck the traceability is established through GPS between the factory and warehouse. Now, within the warehouse is local area network. That's more complicated. But if we have the smart warehouse established, then everything moving like a man, machine, material in the warehouse are traced and tracked. Therefore, we establish the traceability within the local area network. Now, this depends on the specific design of the network. Okay, different local network configuration between different companies will be different. So it all depends on the situation, just like the internet. Okay, now for the catchment area network, traceability is very similar to the one, but slightly more complicated. So at the warehouse, we upload the module to the truck, and that truck send the modules to construction site. Now, the problem is one truck may send multiple modules to different construction site or one construction site. Again, they are monitored through GPS and also indoor positioning system. So indoor positioning system in construction is much simpler because the modules are bigger. So the accuracy requirement is like 2 meters or 5 meters. Now that's easy to do. Now, the local area network at the construction site are very difficult to establish. It's also a line in each construction site. The reason is the building is moving up and up. So the data collector or the gateway, you need to move them up, okay, while the building is, going upwards. Now, when the satellite moves, then you have to recalibrate the location of those routers. So this is why we are establishing calibration-free genetic self-learning algorithm for this purpose. So we basically move the gateway together with the crane or other facilities. Therefore, we capture the data and then establish the traceability within the construction site. So we have to discuss them separately. But it's a good question.
Yeah, I hope George answered your question. Otherwise, you can send in follow-up question for clarification. Now we move on to the next question. Thank you for a great talk, Professor Huang. Could you please introduce more about the PIP physical internet protocol? Is it in development or already developed? Is there some standard related work already on the way? Thanks.
This is a question that we are working on. Physical internet PIP is an extension or a transformation of the TCP/IP protocols to physical internet. Okay, we are developing this. Now, the essence of this is the load packet or logistics packet, the basic unit of loads, okay, unit of goods. That's very, very important. For the moment, there have been debates among researchers, and there isn't any agreement so far. But again, as I mentioned in the middle of the seminar, we are developing a logical container or packets for the goods or logistics. Okay, it doesn't matter if it is box or trolley or pallet or container. Okay, that's extremely important. We are developing these. These are not too difficult to develop, but it's very difficult to convincing the industry to adopt and use. Now, for the standard part, we are forming a working group aiming to establish a IEEE standard for the TCP PIP. We will invite major logistics companies to join this working group. We already talked to IEEE for this, and we are setting up the working group for the moment. Hopefully, by the end of this project, we can establish an international standard through IEEE.
Great. Now let's move on. This looks like it's a comment. Security is the main problem with the CPS system. To come up with a way to make these systems more secure in an efficient way is the biggest problem, but not rigid, fixed to one form of a system. So this is a comment. So let's move on. I'd like to ask Professor Huang, can you use reference tag for realize more accurate positioning?
It's early days, people use Wi-Fi, RFID for indoor positioning, but the accuracy is not good. And people are using, like Huawei, proposing the 5G indoor positioning, and they claim they have achieved good performance. But I think the reality is the accuracy is very limited. For the moment, we use Bluetooth beacon and also UWB. It's a trade-off between the cost and accuracy. So if you want a very high accuracy, you use UWB. But the cost is much higher, 10 times higher or 20 times higher than Bluetooth. So for the moment, we use Bluetooth for our industrial partners because the cost is acceptable and also accuracy is adequate for the application. We can achieve like 2 meters for the moment for the indoor positioning. 2 meters are mostly adequate for manufacturing, especially construction and warehouse applications.
Okay, great. The next question, how would this system, when implemented, practically affects the economic impact of new crises, such as a new COVID wave?
Now, if this CPI is successfully implemented, then we can use something like a ping command or trace, like what we use with the Google Map for searching for the path. We can use CPI to ping the connection between different locations. If this one city is locked down, then basically that path is blocked. CPI will tell you. And if there's something going on, for example, today in between Russia and Ukraine, then that train is stopped. Our train, Euro-China train will be stopped. So the ping will tell us it's not connected. So find some other way to go. At least we will get the first-hand information during this time window. Okay. Tomorrow things will be changing. So tomorrow we'll use another time window, special temporal window to make decisions. Okay. So this would be very useful to achieve the resilience of global logistics system.
Now, the next question is a sharp question. The warehouse localization problem is solved. Ocado and other big automated warehouse system can localize all types of goods inside warehouses. What is the difference here?
Now, this is actually a good foundation for us. What you are saying is we have a good local area network because we consider warehouses as a local area network. So if they are excellent, automated, that means this local area network has been well established. But for global logistics, it's not just warehouse operations. We have operations in between factory and warehouses, warehouses between distribution centers, distribution center between wholesalers and retailers and consumers. So the global logistics systems are far more complicated or far wider than warehouse systems. As I said, this is good news. This is also why we have the confidence to develop CPI. Okay.
Yeah, last sort of question on my screen. What are the policies in place to drive this process, looking at cross-border logistics?
Now, this is actually very important, very sophisticated question to answer. The previous European projects on physical internet, between EU member countries, the border controls, basically there are no border controls, and the currencies are the same, euros. But in the CBA, GBA, in Hong Kong, we have real border controls between Hong Kong and China. We use different currencies. We have different law systems. Everything is different between Hong Kong and China. But the intensity of logistics services is very, very high, okay? And all the policies are different on both sides. Now, again, if we use the analogy in internet with the data, okay? So, but data are much simpler. They do not have the safety and security. What I mean is like the weapon. Now, for the logistics, the goods can be weapon or drugs. Okay, they are very dangerous. But for email data packets, we don't have this problem. So there will be border issues, okay, between different countries. And this is something probably we were, for the moment, ignore for the moment, okay? We focus on the technology part for the moment. The policy part, we cannot deal with it for the moment. Yeah.
We have the last sort of question here. Thank you for the great talk, Professor Huang. Can we learn more about the suitable application scenarios of CPI besides agriculture?
For agriculture. Now, for agriculture, we had intensive discussion or extensive discussions with the agriculture or industry, if you like. First of all, like the harvester, the scheduling, the shared scheduling among the agriculture machineries, harvester, and those are basically rented, okay, in many countries, okay. So there are, this is actually a good example to do, but we do not have a track record. We only discussed with a few harvester manufacturer, and we also discussed with farms of Chinese medicine, okay. Chinese medicine, the traceability is extremely important, from the farm to the harvest and logistics, warehousing, distribution, and the production and the distribution of the medicine. Okay, the whole life traceability. Again, we discussed, but I did not include this scenario in our project. But if you are very interested, you can work on or propose a project on CPI for agriculture. Very important. Food traceability. Yeah.
Great. So thank you very much. It's time to wrap up this keynote session for today's webinar. Before I wrap up this webinar, I would like to thank Professor George Huang again for delivering this wonderful, excellent keynote talk today. Also, I wanted to use this opportunity to thank all the online participants for your participation in the question and answer question. If you have further questions, you can reach out to Professor Huang for further clarification. For now, I would like to close this session. Thank you for your listening, for your participation, and future AI for manufacturing webinars will also be announced online. Please monitor the announcement from time to time. You will also receive announcements through your emails. Please stay tuned. Have a great day, and bye for now. Bye-bye.
Okay, very much. Bye-bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
AI is a powerful tool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.